Okay, so welcome to the next class. Before I begin with the topics of what we're going to discuss today, let me remind you that there was a class which uh, which discussed the experimental verification of the Maxwell-Boltzmann speed distribution. So that those topics is also discussed in RIFE section 7.12 and in particular refer to figure 7.12.2, and so these two figures. So this was discussed not from RIFE but from some other sources which I found on the web. Though the Maxwell-Boltzmann distribution was derived, or people knew about it from kinetic theory from, I think, sometime late 1800s. The experimental verification, I think, was done by Eldridge, Eldridge, sometime around 1927. So the challenge is, of course, that the air is made up of gas molecules, which we can't see, and not only you have to figure out. You have to figure out its position, but also measure its velocity of extremely tiny particles. So the broad question is, how do you sort particles so that your detector detects only the set of particles which have velocity between speed or velocity, depends upon what you're measuring, between v and v plus dv. So this point was discussed in class and it's anyway there here. I'm not going to record this part. So today's discussion is going to be more about quantum statistics, and in particular, we're going to read soon something called the distribution functions. So what is a distribution function? In the past, we have discussed distribution functions, but those was in the classical sense, a bunch of particles. So distribution function, what we discussed in the past, was at position r, at a certain position r, in a certain volume, um, which has the volume is small but large with respect to the number of um, gas molecules that it contained, and the distribution function told us about the number of particles at position r which are traveling between velocity v vector and v plus dv vector at a certain point in time. So that was the distribution function classically. However, distribution function in the quantum statistics context is something else. It's basically tells you about the mean number of particles in a particular quantum state S. More about it in soon. So this is basically matter which is taken from RIFE section 9.1, and just to tell you that for a ith particle, to specify its quantum state, you have to specify all the quantum numbers. Suppose it can be position of a particle, that can be a quantum number, or a momentum. What is its momentum value? That can be a quantum number. Spin state. So, and you have a wave function. And if you specify, you either specify the wave function or you specify the quantum numbers, and that will specify the quantum state of a certain particle. But in general, there can be n particles in a system and they can be interacting with each other. And then the state of the system has to be specified by a set of quantum numbers S1, S2, S3, S4, and so on and so forth, right? And so let Si denote the set of quantum numbers of a single particle I, and in general, there can be n particles, right? And then you have to specify the quantum numbers of each of the n particles, and then you have defined the quantum state of the entire gas, right? So you have to specify the quantum numbers of each of the n particles, and then you know what is the quantum state of the whole gas. Just to have a picture, suppose there's some quantum states which are defined by say energy E1, and it can be in spin. Another quantum number is suppose the spin, and it can be S1, and there is a separate quantum state with energy E2 with spin say S2, like plus half or minus half, and then there's a certain other energy level E3 with energy E3, and if you specify its quantum number S2 and so on and so forth, right? Now, these quantum particles are indistinguishable in that if you interchange, suppose this particle and this particle uh, between this quantum state and this, or whatever, suppose this, because this is the same S1 spin, or whatever be the quantum number, then the two on interchange, you get the same quantum state of the system. So exchange of two particles does not lead to a new quantum state. And suppose you have multiple copies of the same system. Yeah, so you have a system. So it might be, so it will have a certain number of particles with a certain set of quantum numbers, and a separate different number of particles with another set of quantum numbers, and so on and so forth, right? Of course, for fermions, the number of particles can either be 0 and 1, but for bosons, it can be higher. So basically, so this S1 actually corresponds to a set of quantum numbers which will specify uh, the state of that particle, um, right? And so basically, different quantum states or energy levels, if you like, different quantum states are occupied by different number of particles, right? So you can have different number of particles. So there are various uh, energy levels, if you like. You have different quantum states, and some particles are in this quantum state, and so the quantum state of course defined by some Hamiltonian. So the quantum state is defined by the Hamiltonian and the boundary conditions, and then the system. Uh, so then a particle can be in one of the different quantum states, and if you have n particles, you could have 0, 1 for fermions, or 0, 1 or more for bosons, particles occupying the same, uh, suppose, quantum state, right? I mean, it depends really on the system and the Hamiltonian and so on and so forth. And if you manage to specify how many particles are there in a particular quantum state with a set of quantum numbers, say S1, how many particles are there in 2 with a set of quantum numbers S2 and S3, that essentially specifies the quantum state of the entire n particle system. Now, you had multiple copies of the system, and uh, and uh, basically what will happen is uh, that due to a small perturbation Hamiltonian system can go from one quantum state to the other. Of course, the state has to be specified by a H0 major Hamiltonian, and there can be a small perturbation which uh, takes the system from one uh, n particle state to the other. So you would have a different set of n1, n2, n3 particles in different quantum states, S1, S2, S3, right? So the n particle quantum state, right? So you had a set of energy levels, a set of quantum numbers defined by the Hamiltonian, and now we are really talking about a microstate. So the microstate, or the quantum state of n particles, will be defined by the values of n1, n2, n3, n4, n5, the number of particles which are in these different quantum states. S1 is corresponding to different set of quantum numbers, S1, S2, S3, and so on and so forth. So that's the picture you are having. And in general, the aim of to calculate this ns bar is to calculate the mean number of particles in with a certain set of quantum numbers, say S1. So suppose there's a single particle state, right? So and uh, yeah, single particle quantum state with a certain set of eigenvalues, and the aim is to calculate the mean number of particles which have uh, uh, which occupy a certain quantum state, and in specification of n2 n1 n2 n3 specifies the quantum state of n particles. That's the micro state. That's equivalent to a micro state. That's equivalent to saying that I mean, classically it corresponds to specifying the position and momenta of n particles. Here, for n particles, you specify how many particles are there in these different single particle quantum states. Before we further go on, I just want to tell you that so I've also kept classical particles in which pair of particles is distinguishable, right? And suppose there are two single particle quantum states, no, there are two particles. There are two particles and in three quantum states. Yes, these are 1, 2, and 3 quantum states. They have suppose different energy levels, three different psi functions, right? And uh, and for fermions, you know that each single particle quantum state can be occupied or by only one particle, right? So if one of the particles is here, then the second particle can be either here or here. So this would correspond to one microstate, quantum microstate. This would correspond to another microstate, and this would correspond to another microstate. And for bosons, however, the same state, the energy state, let's say, to be specific, can be occupied by two particles. So they can be they're occupying the same, and they have the same energy, say they're occupying the same quantum state, and hence in terms of the microstate or n particle quantum state, they can be like this, or both can occupy level 2, or both can occupy level 3, or they can be separated in such a manner, and so on and so forth, right? uh, whereas whereas uh, for classical systems, if those existed, then a particle A being in, say, level 1 and B being in level 2 is different from B being in here and A being here. So these are two different n particle quantum states. But here, if you interchange them, it wouldn't make a difference, right? If they were identical particles. But here they are distinguishable. They might be identical, but they are still distinguishable. And if you calculate the probability that particles are in the same state, same quantum state, versus divided by the probability that the particles are in different state. So this zeta, in this case, for fermions, particles have to be in different states. So hence this ratio will be 0/3, because there are three states three n particle state, three microstates, if you like, where the two particles are in two different quantum states. Here, on the other hand, you have three of these where they are clubbed together, they are bunched together, and three others where they are separated. They are occupying two different energy levels. See, whereas here there are six ways in which, in the classical case, though that doesn't really correspond to reality, but still, just for the sake of it, for the sake of comparison, there are six ways that two particles can occupy different energy levels where they are, I mean, they are different, right? Uh, they have different quantum numbers, if you say, if you like. So, so basically, the point is that fermions like to spread out, occupy different states, right? Uh, when there are multiple particles. On the other hand, bosons prefer to club together, bunch together. Now, the energy of the microstate is now specified. So ER of the microstate, and there has to be transitions from one microstate to the other, which will be through a perturbing Hamiltonian. So basically, if there are n1 particles in energy with energy epsilon 1 and two particles with energy epsilon 2 and so on and so forth, and ith particle with energy epsilon I, then the total energy of the system can be written in terms of, so uh, R equal to, I mean, okay, so so energy level is starting from 1 and ending at whatever be the total number of energy levels, if you like, or different quantum states. So NR, epsilon R is the total energy of the system, and specification of the different values of NRs, which means how many particles are in which different uh, and with different energies, that specifies the statistical state of the system, right? Now, the partition function is a sum of different microstates, and different microstates correspond to different combinations of the values of n1, n2, n3, n4. But the total number of particles has to be conserved in most cases, except for that of photons, because photons can be created, can be generated. Yeah, I mean, matter can release photons. So the total number of particles is not conserved in this case. Uh, so for for the photons, if we have to calculate the partition function, we have done this before also, but I'll just quickly repeat it. The calculation of partition function involves the sum over different microstates, where different microstates have different numbers of particles with energy epsilon 1 and 2, again can vary from 0 to infinity, I mean a very large number, and so there are into number of particles with energy epsilon 2 and so on and so forth. But since particles can be created or destroyed and different, so we don't consider interaction. So basically, for each energy level, suppose the photons in a quantum state with energy epsilon 1, and the number of photons which can be there with energy epsilon 1, it can vary from 0 to infinity. And similarly, that is exactly the case for with photons occupying a quantum state with energy epsilon 2 and so on and so forth, epsilon 3 and epsilon 4. Now, each is a GP series, right? And hence you can use the formula, and one runs from 0 to infinity, where infinity corresponds to a very large number. Of course, there will be lesser and lesser probability if the energy becomes higher and higher, but whatever be it, um, the sum of this series is 1 upon 1 minus e to the power minus beta epsilon 1. The sum of this series is 1 upon 1 minus e to the power minus beta epsilon 2, and so on and so forth for each of these terms. And then log of z. So if you take a log, each of these products will become sum, and hence log of z will be minus, because it was in the denominator, sum over r, so over all the different states, quantum states that are there, ln 1 minus e to the power minus beta epsilon r, right? And then, as we have seen before, the average number of particles can easily be calculated as minus 1 upon beta del del epsilon s, because yeah, I mean, this taking this del del epsilon s will result in, so suppose you do a del del of epsilon s of this log z, uh, then what will, yeah, what will what will come out here is beta n1, right? So that will, and if you have that with the right probability for a particular energy, right, and so then you will get the mean number of particles corresponding to that uh, that energy level. But of course, for a certain, so what you are calculating is there are these different microstates, and when suppose there are n1 particles in a particular microstate, these numbers can be different, and those will correspond to different microstates, right? So you really have to give a weightage, right, probability for different microstates, and for those microstates there will be a certain number of particles in, suppose, energy level epsilon 1, and then you are taking a suitable derivative with respect to it. So in that case, I mean, so because this n bar s, as you know, is 1 by z ns, you're taking if you take a derivative with respect to del epsilon s, then what you will get back is beta n1. So that's why you have an extra beta here. And for the photon case, it's pretty easy to calculate because total number of particles is not conserved. So you have an infinite GP series for each of the terms. Yeah, so that's what I had to say. And then n bar s basically stands for minus 1 by beta del L epsilon log z, as we have seen. I mean, this is the details of the calculation. However, for Fermi-Dirac statistics, it's a bit more complicated, and we'll look at it, and we'll continue from here in the next module, I mean, next lecture or something like that.